Okay, so in the first lesson that we had first looked at what a set is, and after looking at a set, how we are going to denote set in this course. And also we looked at the ways of representing a set, that is by listing and by roster form, which is a listing. And also we looked at the other method, which is set bidder notation. So now these questions here have been given in a bit of form like set bidder notation, and then we are being told, or the question here is to list out what these sets are. So we'll begin here first. Then after doing this, questions on listing and set bidder notation, then we will now build up to what we're supposed to look at today, which is set operations. If you have any question at any time, at any point, please feel free to ask. So the first question is, this is telling us that X, we have the set of OX. So I'll maybe name all these sets just A for easy annotation that it's set A. I'll be calling it set A. So this set here, set A, we're saying it's a set of OX. This bar here that you see is such that, or it can be written as two dots like that, such that X is a natural number less than 5. So I have to list down. So these questions just for listing. Set A is a set of natural numbers that are less than 5. So what natural numbers are less than 5? So I'll say A is equal to anyone who the numbers, okay, to cut on time, the numbers that are less than 5, the natural numbers, which are just numbers, the counting numbers starting from 1 to infinity. That's 1, 2, 3, 4, all the way going up to wherever we don't know because it's infinity. So now those that are less than 5, that is 1, 2, 3, and 4. So these are the numbers that are less than 5. Part B is saying, or part 2 is saying, set of OX such that X is a negative integer greater than -3. A negative integer greater than -3. So what is this negative integer that is going to be greater than -3? So when I look at negative integers, I have both positive and negative natural numbers. Negative and positive natural numbers, those are integers, now including 0, of course. So now when we are looking at this question here is telling us the key part, that X is a negative integer greater than -3. So I'll say A is going to be equal, I look at what numbers, what negative numbers are greater than -3, what negative integers are greater than -3. So we know that as we are going to the negative side, to the negative part of the number line, that numbers are reducing in size, whilst when we are going to the positive size, they are increasing. So meaning those that are greater than -3, it is going to be -2 and -1. These are the ones that are greater than -2. Then part 3, they're telling me that uh, this is a set of OX such that X is a positive number less than -5. So positive number less than -5? Well, is there any positive number less than -5? Of course, there's no positive number less than -5. All positive numbers are greater than -5. So meaning this part of the set is just empty. And as we said in the previous class, that this would denote empty, or when we just say two braces like this without anything inside it, it will be an empty set. So this side here is the empty set. Then union this side here. So the empty set union, the set we have here will just be that exact set there. So meaning this here is just going to be A, we'll say is going to be equal to 1, 2, and 3. Since this side is empty, so you have nothing, right? Then you get something, then you put everything together. Then what you have there is what you have, the something that you had is what you're going to have. So if I have 3 pens in my hands, in my right hand, then in my left hand I do not have any pen. Then I put my hands together, I hold the pens together in both hands. It means what I have is just the 3 pens. So this is what we are just doing here. Then Part 4 is saying x is a positive even number less than 10, then intersection. So already you'd see here that we've introduced the union and the intersection, which are set operations. Well, if you don't get them, wait, hold on to your seat. You're going to get them even as we progress and look at them in further detail. So we are saying that uh, x is a positive even number less than what, 10. So when I look at 10, even numbers that are less than 10, to list them out, the even numbers less than 10, there's 2, there's 4, there's 6, and there's 8. These are the even numbers that are less than 10. Well, even numbers positive only. That is, then they're saying intersection. Then intersection what? They're saying x is an integer. So x is an integer, and integers, of course, I know I have from negative values here. I only write, so this is from negative infinity going, I only write -2, 0, the 1, then going this way. So this is the whole set of integers that they are having. But then you're intersecting, and intersection, what just that intersection means is what is common in both. But when you look at this set now of integers, these even numbers here will also be there as you go this side. So what will be common is just this part. So listing out on question 4 what they're asking for, meaning our A is just going to be 2, 4, 6, and 8, like that. So this is what you get. On question number 5, which is, or part 5 is what we are going to next. So now for part 5, they have said x is a set of all x such that x, so x has been given a formula. So x has that formula, which is 4k minus 1. But they're telling us k can take on values. So k is a member of this E, like that, means member of. If it is not a member of, then you'd cross it like that. Okay. So what this then means, saying k can take on values from 0, 1, 2, up to 5, like that. Those are the values that it can take on. So meaning we need to replace k and find each and every value of what, of x. That's starting from k equal to what, to 0, going all the way up to 5. So starting with the first one, when I replace when my k is 0, if I have 0 here, so meaning I have 4, 0, negative what? This I multiply just gives me what? Gives me 0, then I remain with a -1. So -1 is what I get. That's the first value there. So I'm going to erase this part, erase all this here, that we have more space. Then next, the next value of x is going to be when k is 1. So when k is 1, I place 1 here. So I have 4 minus the -1 gives me what? Gives me 3. So I get 3 there. Then when when k is 2, this here will give me 8. So 8 minus 1, I'll get 7. Then I go when k is 3 minus 1. So when k is 3, I'll have that this is going to be 12. 12 minus 1 gives me 11. When k is 4, then I'll have 16. 16 minus 1 gives me 15. Then when k is 5, which is the last number, 4 multiplied by 5 minus 1, 4 times 5 is 20. 20 minus 1 gives me 19. So these are the values that I'm going to have for x. So to list out this set, which is on part 5, meaning which I'm just calling A in this case, is just going to be the values that I had here. So -1, 3, 7, 11, 15, and 19, like that. So this is the set that I am going to have there. Okay, so from here to do the last part. So the last part then is just telling us, for the last part, we have that it's saying set of OX. For the first part they are saying is an integer. X is an integer. So the same way we had listed integers, just list the first ones. That's, I mean, only this part, like that. Of course, because I know they're going, okay, I've listed them the opposite way. So the negative here shouldn't be there. So 0, 1, the negative should be this side. So like that, then all the way to positive infinite, going like that, there to the positive side of the numbers. So this is what I have for the first part. And they're saying intersection, meaning they're asking me what is common with this thing here. Intersection just means what is common. So when I look at here, I have to look at which ones are the integers. So the first one is an integer, and then also 7 is an what? Is an integer. So here we have this root 2, then 3.14, then 7. So this here, 1 is an integer and what? 7 is an integer. So the intersection here in here is just going to be 1 and what? And 7. So this one here, root 2 is an irrational number, which we'll look at further as we go and look at proving irrational numbers. And also then this one is a rational number. So the difference is that this one here can be expressed in the form A over B, where B is not equal to 0, and A and B are co-prime, meaning that they do not have any common denominator. Well, if it looks confusing, you understand it better when you look at irrational numbers and rational numbers. I also send a link to irrational and rational numbers in the group that you watch that video. Yes, is that the question? Okay, I guess, is that a question? You can go on. If it's a question, you can ask. Okay, I bet that's not a question. All right, so we continue. So continuing now, the next set of question is this one here. They're telling us to list, so listing elements from a given set. So the given set is here. A is -2, -1, 0, 1, and 2. Saying list the elements of each of the following what sets. So these sets, then based on what? The numbers that are what at an A, because it's saying what we have is that it's defined for the first one, it's defined as x cubed, given that or such that x is a member of what? Of A. And when I look at what A is from -2, -1, 0, 1, and 2. Then they're telling me to list out this set. Okay, is that a question? If you are not asking a question, you can mute your mic. If you want to ask, just unmute then speak. Okay, I don't think that. Okay, so continuing. So we have x cubed. So we have a polynomial of degree 3, or a cube root, a polynomial of degree 3, meaning that's x cubed. That's x raised to the power to the power 3. So then now they're telling me that since x is a member of A, so what will that mean? I need to find for each and every value. So -3, I'll raise it to the power what? I mean -2 raise it to the power 3. And this means -2 times -2 times -2. But then because you know that if the power is odd and you have a negative sign, meaning it will give you a negative. And then, okay, who is this writing on my screen? Okay, just a minute. All right, so we continue. So this is -8. Then the next one is -1 to the power 3, which is just going to be -1. 0 to the power 3 is just 0. Then we are getting from the set A there, don't be confused. Then this to the power 3 will be 1. Then you have 2 to the power 3 is just what? 8. So this here is the set that I'm going to what? I'm going to write out. And that set there is just going to be -8 being the lowest value I have, then -1, 0, 1, and what? And 8. And I have listed it out just like that. Okay, so you do the same for this one. I'm going to leave this one for you to do. It just follows with the same concept that we have done. And then we will do part 3, which is kind of a different one because you have a rational function. So a rational function is just where you have kind of a division here. You have an x, the x is down in the denominator like that. So here we continue, we do essentially the same that we are doing, which means we have 2. For the first one, we have -2. So we have 2 here, then we have -2 plus 1, and that there is going to give us a -1 down. So you have 2, -1, you divide, you get -2. So the first value I have is -2. I keep that well. Then for the next one, you see that for the next one, we have -2. So when we put now, for this one, when you have 2, then you have -1 plus this here cannot happen. This is undefined because you get a form where you have 0, 2 to the power 0, and this is undefined. So meaning at -1, we have no value. This is undefined. So we cancel this, so we leave this out. Always, when you start looking at rational functions, you always demand that the numerator, I mean, in the denominator, you should not get a 0 because that will give you something that is undefined. So you exclude the part which makes it undefined. Then we have the next one, which is 2x is 0. Then you have plus a 1, and this is just going to be 2. So the next value there, I write 2 here. Then for the next one, what do we have? So for the next one, we have 2 over x is just what is, so a 0, oh, 1. So 1 plus 1, this gives us 2. 2 divided there gives us 1. So I have 1. Then the next one is just 2. I'll have 2 here, and that gives me 3. So this gives me 2 over 3. So I have 2 over what? Over 3. So now I will write this out in my set. So this is going to be, I'm taking it. So this set here, part 3, is just going to be, I list from the lowest in ascending order. So that's -1, 1. Then I have, okay, so whether you list it in the in ascending, or you list it the other way around, where you the way in which you were finding them, it will still be okay. So you list it like that. Also, the last one is just 2. So you have -2, 1, 2 over 2, then you have 2 like that. So this here is your set. For the next one, you just apply the same concept that we did. You try this one, because here you're just replacing the values and getting the way we were getting, and you list out the set. Okay. This leads us now to our final part of the question that we finish up on, what we were essentially looking at. So now this tells us to describe the following in set beta notation. So we have to describe using the shorthand form which was given in part 1 of the questions we're looking at. So we use that kind of shorthand way of writing, in which I should write these. So we have set A, and set A, when we look at the numbers that are in set A. So I have 1 here is the first one, 4, 9, 16, and I have 25. So when I look at this, I'm saying it's a set of OX such that, now what is X? So X, when you look at X here, X is just, is a number that is being squared. Because when I get 1, I square 1. So when I get 1 and square 1, it gives me 1. Then for the next one, I get 2, I square 2, this gives me 4. For the next one, I get 3, I square 3, this gives me 9, all the way up to what? Up to 5 in this case. So then this means x is equal to n squared. X is equal to what? To n squared. Then n, what values is this n? I just said it's a number. You could put a here, you could put what, but then you have to define what values this n is going to take up. So n just takes on value. So n is a member of what? I can list those numbers. So the numbers that it is a member of, that is n is a member of 1, or you could just say n, like n is equal to, then you say 1, 2, 3, 4, and what? And 5. You could write it like this. Or if you didn't want to write it like this, and an alternative would be writing x such that x is equal to n squared, then you're saying this n, I know this n is a natural number from here. So this n is just a natural number, and this natural number is what is in between. So this natural number is from 1 to what? To 5. So it's from 1 to 5. So you indicate it that way, saying it's from 1 to what? To 5. So this means it, since it's a natural number and you know all the natural numbers from 1 to what? To 5. So we would know that there's 2, there's 3, and there's 4 there. So writing it like this or writing it in the first what still be okay. Okay. Uh, hope we're still together here. I hope I haven't lost anyone. Okay, so next we have B here, and B is just saying, so B we have -5, -7, -5, -3, and what? And -1. So now when I look at those, what are they? So I'm going to get two approaches as well here. We'll write it in two forms. So the first one is going to be, we're saying X such that X is, we are going to define X by what? By a formula. So when you're looking at even numbers, you'd say they're numbers that are divisible by 2 and they don't leave a what? A remainder. So when coming up with even numbers, meaning you're just multiplying n by what? By 2. But then when you're coming up with odd numbers, yeah, making it odd by adding what? By adding a 1. So we see that these numbers here are odd. They are odd, but they are negative. They are odd numbers because when I divide by 2, they leave a remainder of what? Of 1. So they are what? They are odd numbers. Then, uh, but they have a negative. Of course, this formula will apply, but then it has to have a negative in front of it. So X is going to be equal to negative 2n plus 1, like that. So this gives me the odd numbers. But then what is my n? My n, what numbers are there to be my n? So my n is just a member of, so the first one is what? Is 0. So the one which gives me the -1, of course, not that it's the first one, but the one which gives me the -1 is 0. Observe that when I put 0 here, when we have 0, when n is 0, meaning 2 times 0 plus 1, this here gives us -1. Then when n is 1, when n is 1, you have negative 2 times 1 gives us 2 plus 1. Then this gives us -3, which is what? The following, which is this side, with this number here. So all the way up to what? Up to 3. So meaning this n is just a member of numbers that is 0, 1, 2, and what? And 3, like that. Then I would close here. So this is how you'd come up with this one. Or you would just state it to say B is actually X such that this X is an odd number. So X is an odd number, since I know, or we know what odd numbers are, or odd, in this case, it's an odd integer, an odd negative integer though, an odd integer, and then you are going to what? You're going to specify that, and it is in between what? -7, -7, and what? And -1. So we know all the negative odd integers that are in between here, because we know that they, when we divide them by 2, they will leave us a remainder of what? Of 1. In this case, since they are negative, when we divide them by 2, they will give us a remainder of -1. So that's how you come up with this set here, or this is how you write it in set beta notation. For the next one, you have that, so we have this part here where we are saying C. So part C, when you look at C, for C, you have 2 here, 4, 6, 8, 10, up to 16. But what are these? These here are even what? These are even numbers. These here are what? Even numbers. So now, by the formula of how we come up with even numbers, it's just 2n. Like that. That's even numbers. And then where are they starting from? So n, what values can n take up? So n is a member of, so n takes on the values of what? 1, of course, when I put 1 here, I get 2, which is the first number. When I put 2 there, I get 4, which is the second number. I put 3, I get that one there. When I put 4, I get 8. I put 5, I get 10. I put 6, I get 12. But then it goes 16. So 16, when I put what? 8. So I'm not going to go 7 because there's no 14. So I go at 8 because the last number is what? Is 16 there. So this is what I get. So now I can write this to say that X, so C is going to be a set of OX such that X is equal to 2n, and I'm saying n is a member of, or is n takes on the values 1, 2, 3, 4, 5, 6, and 8 like that. So these are the values that it can take up, and that's how you write it in set beta notation. Last one, but not the least, of course, uh, we are saying that this one here, when we look at this one, we have 1, 2, 4, 8, 16, and 12. How are they coming up with these numbers? So these numbers essentially are, so when you look at them, they are coming up with these numbers. All these numbers here, 2 can divide into all these numbers. And when you see that if I am raising 2 to whatever power of the number is, so 2 to the power n. So if 2 is 0, that's when 2 is 0, I mean when n is 0, you have any number raised to the power 0 is going to be 1. So that's the first number there. Then when n is 1, any number raised to us is 1 is just going to be that same number, which is 2. Then the following number is 2 raised to the power 2, which gives me 4, and so on and so forth up to n taking on the value of what? Of 5. So 2 to the power 5 will give us the 32. So this then, I'm just going to write that it's a set of OX such that x is equal to what? 2 to the power n, and then n can take on values from 0, 1, 2, 3, 4, and 5 like that. And just like this here, I write and have written in set beta notation. Well, I don't know if there are any questions on listing and set beta notation, but essentially we are done. We now want to look at a different concept. Are there any questions before we continue? Okay, so I presume there's no question and that is clear. So next we're just looking at set operations. So earlier I did share with you a video on this and I hope you watched. So set operations, we essentially talk when we have two sets. So when you have two sets, let's say I have set A and set B, union. So just the same way like in arithmetics, you would add, subtract, and multiply. With sets, we can also do such operations, which we're calling set operations. And how we do them, of course, um, is by the union, the intersection, complement, and set what difference. So the union, what this means is, so, and then here also we are going to introduce a concept of what? Of Venn diagrams. So these sets can be shown in a pictorial form. So this here, this box is what we're calling a Venn diagram, and E here represents this here, everything that you see here is the universal set. That means it contains all elements. The set that just contains all the elements that universal set. Then our sets will sit here. So if we have a set, maybe we have two sets, A and B. So A and B are going to sit there. Now, what the union does, okay, so what the union of these two elements of these two sets does is it's considering elements that are in A or that are in what? That are in B. So I'll write it here. So A union, it's represented by this symbol here, union, like this. Looks like a U. So easily to remember because that's union. So this here is the set of OX such that X is a member of A or X is a member of what? Of B. So X can either be in A or X can either be what? In B is what you are talking about. So meaning that this is kind of joining the whole set together. So when we are shading, let's say you're told to shade A union B, meaning you would have to shade what this whole part here, because you're saying the element is either in this part, which is A, or in this other part, which is what, which is B. But then the union would mean the whole thing then, because it's either in A or in B. Okay, we're moving on to intersection. So the intersection, so A intersection represented with an uh, more like an N like that. This here is saying that is a set of X such that X is a member of A and X is a member of what? Of B. So this means that X is in A and is in B. So it means it is common in both of what of them. So that part when you're shading is going to be this middle part, because this middle part has those elements that are common in both of what of these sets. Okay. On the other hand, now we are going to look at the complement. I erase this. I'll draw another one. So, okay, suppose I have one set like that, that is A, and this is the universal set. Then we're talking of a complement of a set. So the complement of a set is going to be denoted either like this with a C, or it will be denoted A with an apostrophe, or with a prime symbol there. So like that, it's going to be denoted that way. But what this means is all elements that are not in that set, all elements that are not in that set but are in the universal set, all elements that are not in the set but are in the universal set. So in this case, a complement, as we have written, we are saying that it it is all elements that are not in A but sit in the universal set. So meaning when you're shading outside what A, and you shade the part which is the what the universal set there, like that. You shade all that part, all that part, all that part there, everything like that. Okay, then the next one where we are looking at is we are looking at set difference. So the set difference of A and B, which is written like this, A minus B, or it is written A slash B. This is just set difference. It's not that you're subtracting, but it's a set what difference. And what this means here, so this also you see it would be written as A intersect B complement. A intersect B complement, like that. This is set difference. So what this means, let me draw my Venn diagram here. Okay, we have set A and set B and the universal set there. Then I erase this part. Let me write it first in set beta notation. So A, set difference of A and B. This is a set of OX such that X is a member of A and X is not a member of B. So X is in A, but X is not in what? In B. X is in A, but X is not in B. And when we shade that, it's going to be just this part here. So you leave out B because it's not in B, but it is in what? It is in A. So this here is the set difference of A and B. So these are the basic set operations that we are going to use. Okay, so is there any questions so far on these set operations? Okay, there's no question. So we're moving on here, just applying what we have learned. We say, saying let A be given as numbers 1 to 8. B, you have 3, 6, 9, 12, and 15. And C, you have 2, 5, and 7. Then they're asking for what is A intersect B. Anybody to answer this? What is A intersect B? I'm waiting for the answer. What is A intersect B? Feel free, just unmute yourself and give out the answer. What is A intersect B? Okay, so from okay, somebody says 3 and 6. So let us check if 3 and 6 is what is in the intersection. So when I look here, the intersection means elements that are common in both sets. And of course, you have 3 there, and you have 6 there and 6 there. So 3 and 6 is correct. So 3 and 6 is correct. Okay, what is B union C now? What is B union C? Okay, B union C. What is B union C? Okay, so B union C just means that you're combining all elements, or you're saying elements that are in B or in C. That just means you're bringing all elements B that are in B and in C together. So here I see I have a 2. So I'll start with that 2. Then 3 follows there, 3. Then I have a 5 from there, so I say 5. Then 6 follows there. Then I have a 7 from here, 7. Then I have 9, 12, and 15 are going to follow. So just combining all those elements together, that is B union C. Then the next part is B intersect C, and B intersect C. What is B intersect C? So B intersect C here, B intersect C is what is common in B and in what and in C. So what is common in B and in C? There is nothing common, so meaning that is an empty set. So I say this here is just an empty set like that. So that's how you'd find these simple questions like that. Uh, well, this video or this link is going to close in the next minute. Rejoin using the same link. So now we want to explain some set laws. Set laws. These are going to be essential when you're dealing or simplifying sets. When you're simplifying sets, these are going to be what to be essential. So the first part is telling us we have a complement. Complement is just equal to what? To A is what they are telling us. A complement, complement is equal to what? To A. So let us, we can show that even using what? A Venn diagram. So if I have the set A here, and then I have, that's the universal set. The complement is here outside. That's the complement of A, like that. So then the complement of A is, if the complement of A is there, then they're saying the complement of what? Its complement. So the complement of its complement, meaning is what is not in this part here. And that part is going to be what? Is going to be this inside part. But this inside part is what? Is just the set what? The set A. Hence, A complement, complement is equal to the set what? A. Then we have this part here where we say A union A is equal to what? To A. So if I have the set A and I'm bringing every element that is in A again together, it's going to just bring me what? It gives me A. Again, if I'm intersecting, what's common in A is also common in A. So meaning that, see that this other part here, which is A, the set difference of A and A. So, or it can be written as A minus A, which is just the difference of A and A. If I was to write my Venn diagram like this, then I have the set A here. Then they're telling me now, this is E, and they're telling me the set difference here. Or you would see it writing this, we could write it also as A intersect A complement. So A and its complement, do they have anything in common is what they're asking. So when you see A, this is the set what A. and its complement, what is its complement? Its complement is outside what here, like that, because the complement means everything that is not in that set but is in the inverse set. But when I look at these two lines that I've shaded, do they meet anywhere? They do not crisscross anywhere. So meaning there is no intersection here. So meaning that the set difference here, that's the reason why it is going to be what? To be the empty set. Set difference is just going to be the empty set. So the next law that we are looking at is the law of commutativity. So commutativity is just here. Commutativity means the order in which I write them does not matter. In the same way, addition is commutative, where we say 1 plus 2 is equal to 3. 2 plus 1 is also what? Equal to 3. The order in which I write them does not matter. So this is what this law is saying when it comes to what? When it comes to sets. To say the order in which I write A union B is the same as B union A. They are commutative. That is only when you are dealing with what? These two sets. Then when you have A intersect B, it's the same as B intersect A. That is what the law of commutativity is saying. So next is associativity. And associativity then you're involving what? Three sets. So three sets, and this is what you're saying. You're saying if you have three sets where you're saying A union B, then union what? Union C. This here is the same as first saying I uh, bring everything together that is in the first two sets, then I bring A in last. So it's the same as saying B union C, then I say A union what? Union A, like this. So that's the same. That's associativity now. Then when it is intersection, it's the same thing where you say, I can, if we're saying A intersect, then I say B intersect C, like this. Then I could do the first two also, that is just saying A intersect B, like this, then intersect what? C. This is what is the associative law. Okay, then the next law we are looking at is the distributive law. Distributive law, it just means I can distribute the sets that I have. So you see that in the first part you have A intersect, then you have B union C. So when you have such different signs, the distributive law just means this I can distribute my A intersect to my B, then I also distribute my A intersect to my what? To my C. So I'm saying A intersect, I distribute it to what? To B, like that. Then in between there's this union, so union goes in between. Then I distribute it again, A intersect what? To my C, like that. So this here is going to be what? Is going to be this here is going to be the distributive law. Also, when it comes to union, if union was outside first, union, then B intersect C is the same or is equal to, I distribute, so I'll have A union B, then intersect, then I have again A union, then I distribute to my what? To my C. So this is the distributive what? Distributive law. Okay, so some of them I'll share videos where I already proved them. Others you can prove them and you can share, you can send the proof either in the group that we discussed, or you can share to my inbox that I am able to check it out. So the sixth law here that we're looking at is A intersect an empty set. A intersect an empty set is going to be what? To be empty. Why? Because if A has elements, and the empty set by definition has no elements, meaning they will not have what? An intersection. There's nothing that is going to be what? To be in common. So meaning that it will be empty. Whilst when we say A union, the what? Empty set is going to be what? A. So when I have something, A contains things, then this one has nothing, I bring them together, it's just going to give me that only that set that had what, that had things. The same way we had done it in the earlier example. And okay, even goes for the what, for the other laws that are what, that are here. So then most of these we'll get to use them even as we go on. Well, this law here is what we had. Okay, let's just look at that one quickly. It's very important. So we have A union A complement is equal to the what, to the empty set. So if I say my A, this is my A, my complement is this part shaded in red. Everything together you see is the what, the universal set, which is the set that contains everything there. Okay, so that is what this here is telling us. Then A intersect A complement. These here, they have no part where they're intersecting because no lines are crisscrossing. So meaning that A intersect A complement is what is empty because the lines there are no common elements that are in between, that are there between A and A complement, which is this part here. Then A union, A union, the universal set is just going to be the universal set because you're saying the universal set has everything, meaning it has A. If I unite it with A, meaning I'll just have the universal set. Then A intersect the universal set. So you see the universal set here, then I have A, then I'm saying intersect this here. You see that I'm just going to what, to have this same part, which is the part what, the part A. So A intersect the universal set is just going to give me A. Well, 8 is what I was rushing to, and 8 here is essentially the De Morgan's laws. Well, don't worry about these ones. We use them also as we go on. But the De Morgan's laws, which we're going to prove next, these are very important. So this here, proving the De Morgan's law. And then I only prove part B. You can do part A, and then send your answer that you're able to watch to confirm. So we're saying the De Morgan's law states the following. So De Morgan's law just states that if I have A intersect C, if I have two sets A, okay, so this here was supposed to say if you have two sets B and C, not A and B. So B and C, then you're saying B intersect C, complement of this is just going to be, if I distribute this, it will be B complement, then the sign will flip to union, then I have C complement. So that's what it's saying. And also if I have B union C complement, then the sign there flips to B complement intersect C what? C complement. So that's what I'm going to what? To have. So I'll only prove the second part, then you can try the other part. So how do I prove it? I'll prove it using direct proof, of course. But what we are going to, or how we are going to say that indeed our answer is true is two sets. If we did not mention this, now we mention it to say, okay, for example, if we just have B and C, so B and C, for them to be equal, for me to say B is equal to C, then what has to happen is that B has to be a subset of what, of a subset of C, and then also C has to be what, a subset of B. So meaning B must be contained in C and C be contained in what, in B, then B and C are what, are equal. So this is what we are going to show for these sets also, that if this part is contained in this one and this one here is contained in that one, then the two are what, are equal. So how do we do that? So first I say let X, which is just an element, to be a member of the first part, which is B union C complement. So it's in the complement. But what does this imply? If it's in the complement, meaning X is not, if X is a member of the complement, it means X is not a member of what? Of B union C, because it's in the complement. So meaning it can't be in B union C. But then also, what does that then mean? So then it follows. So it follows, you could write it follows, or you use the implies symbol again. So it follows that X, so if X is not a member uh, of B union C, then what does this then mean? So this means that X is not X is not in what? In B, and X is also not in what? X is not also in C. Since so if X is not in the union, because union you've brought everything together. So that means if X is not there, meaning it means that X is actually not in B and X is not in C. But what does this mean? So if X is not in B and X is not in C, then it implies that X has to be what? In the complement. So meaning, okay, so meaning X has to be a member of what? Of B complement, and X is a member of what? A member of C complement. But the and there just means what? Meaning it's in both sets, meaning that's intersection. So X is a member of what? Of B complement intersect C what? Complement. So this is the first part. So this then has shows. So therefore, I'm saying therefore, this shows that the B union C complement is a subset of what? Of B intersect C complement. Because I started from here, then I was able to show there that X is in there and also X is in there. So meaning it is contained. Next part is you are going to start with what? You start with this right hand side where you say let X be a member of, so let X be a member of B intersect C. So you can say conversely here just means on the other side of things. We can say we can let X be a member of B complement intersect C complement. So if X is a member of B complement intersect C complement, then what does this mean? So this then implies that X is a member of what? So X is a member of uh, B complement, and X is a member of what? Is a member of C complement. What does that then mean? So this then implies that if X is in there and X is in there, meaning X is not in B, and what? X is also not in what? So X is not in B, and also not X is not in oh, not the complement, but just in B. So here, okay, so X is not in B and X is not a member of what? Of C. So if X is not in B, then it's not in C. What does this imply? It means that X is also not in what? If it's not in B, it's not in C, meaning it's not in the union of these. So meaning X is not in the union of A and what? And C. If it's not in the union, then what does this mean? It means that X has to be a member of what? The complement of B union C. It has to be a complement. I put not a member. Why am I putting not a member here? So it means that X has to be a member of uh, B union C complement. And this here is going to be the what? The proof, and that's how you prove. So you prove even for the next one. So here, since it's not in B and it's not in C, then obviously it's not going to be in the union. Then if it's not in the union, then it means it has to be in the it has to be outside the uh, if it's not in the union of B and C, meaning it has to be a member of the complement of the union of what? Of B and C. Okay, I don't know if there's any question here. Okay, if there's any question here, but this is how you do the De Morgan's laws, and this is how you prove it. This is an easy question that we could show, or we could, so it's saying verify or show that A union B complement is just equal to A intersect B complement. A union B complement is equal to A intersect B complement. So how do I verify? So I have A, so my A is this one and my B is there and my universal set is there. So I have A union B at first. So I start with this one. So what is my A union B? So A union B, I'm bringing everything together. That is in A and B. That's 1, 2, 3, 4. Then I have 5 and 7. So these have brought everything together. But what is going to be the complement of this? So the complement here is everything outside this. So not so this set, everything outside this set, but is in the universal set. So the universal set has been given from 1 to 10. So I look at what numbers are outside this range, and those are numbers that is 8, 9, and 10. So 8, 9, and what? And 10. So this is the first part. I keep it. Then the next part, you have A in A complement. So I find first my A complement. Everything outside A but is in the universal set. So if A is from 1 to 5, then I check everything outside that 1 to 5 is going to be 6. So here I have 6, 7, 8, 9, and 10. So I write those numbers 6, 7, 8, 9, and 10, like that. Then my B, so they're saying intersect B complement. What is my B complement? Everything outside here, B. So 1 is not in B, so I write it here. 1 is not in B, then I have 2 is there, okay, 3 is there, 4 is not in B, so I write 4 here. 6 is not there, so I write 6 here. So, okay, 7 is there, then I have 8 is not there, 9, and what, and 10. Then here I have A and B. So what is A complement intersect B complement? So this here is just going to be what is common in both of these sets, that is 8. So 8 is common, 9 is common. Then I have that, which other one? Oh, here we forgot a 6. 6 here at first, because 6 is outside this range. It's not in this set. 6 is not in this set. So here also, when I look, 6 is common, and also 10 is common. So let me write it in ascending order: 6, 8, 9, and 10. And when I look at the two sets, they are just the same. So A union B is equal to, A union B complement is equal to A complement intersect B complement, hence verified. Hence, I have verified. Well, I leave this one for you to try, and I'll share it in the group that you're able to try this one. Okay, so, okay. Oh, okay. What's happening to my keyboard? All right. So, so we've proved this part. We've proved this part. So these are just more questions on sets. Is what we're saying. So we've proved the first part. Try this one. Try this one. Write a formal proof for it. We see, and see what you're going to get. But you go the same approach where you say let X be a member of this part. Then you show that this is a subset of that, and that is a subset of that one. Next here, we just want to do this one, and I only answer 2 parts. For the next, I'll be answering only 2 parts. The rest, I've put them together as a compilation, as an assignment for you. So we're saying A is a subset of D. So A is contained in D, is what we are saying. So A is contained in D. As a Venn diagram, I draw it like that. Then I have D outside here. Then I have C that is contained there, C. So they're saying what is A intersect what? What is C intersect D? So what is common here, in short, between C and what and D? So C is in D. So when I look at what is common, it's going to be what? This same part here is going to be common in both of them, because D contains this part. So this C intersect D just simplifies to what? To C. That's what we get there. Then the next one, you have C complement union D complement. What is C complement union D complement? So C complement, so when you look at C complement, it's good to have a Venn diagram. So C complement is everything outside C, but is in the universal set, which is going to be that there, like this. Then union D complement. So D complement, this is this part here outside this here. Then you're essentially joining everything together. You're bringing everything together. So in short, everything in blue together. So when you look at that, it's just going to leave us with the set what? With the set C. So meaning this here is going to simplify to the set what? To the set C. Okay, you would have written it also by De Morgan's laws, the way we've from learning. this C complement union D complement can be written as C intersect D, then the complement comes outside. But then uh, this here, what we have looked at, uh, oh, this, okay, so this is not C, this is not C. We look at it, we find it like this, sorry, find it this way. So A intersects C, what we found here is what is C. So C in the complement, because A intersects C, we say this is contained here, so it has to be C. So C complement in short, but C complement is just this part here in blue. Now that part is hard to, describing it in terms of simplifying it in these letters uh, is is hard. So what you can just say is just C complement. It just simplifies to C complement like that. Then you know that it's everything outside what outside C like that, and nothing like any form of this. So it simplifies only to C complement, and you leave it like that. The rest of the two, as I said, I'll leave it to you guys. We do here the two. So these two here, they're saying they're disjoint. So when two sets are disjoint, it just means they do not have any intersection in common, meaning I have set C here and set D there. Then they're telling me what is C. Okay, so C complement intersect D complement. So I can write that. I know that C complement intersect D complement. This here is just equal to what? This is equal to C union D complement. So so C union D is this here. Everything in C together with everything in A. Since you're saying in D, I mean, since it's in A or in D. So if this here is what, then the complement is everything outside here. So the complement is going to be outside, outside there like that. That's the complement. So the complement, meaning what remains is just the what, that part of the universal what, the universal set. So you can write that. So if you write it like this, it would be okay. Or you would write, you'd write it as the universal set, which is either E or U. Then you're saying mm, minus, so minus what? Minus, which just means you're removing the complement. So complement of C union what? Union D like this. Or when you look at this here, you could just leave it even here like that. That's still in the simplest form because you can't go any further here when it comes to simplifying. Um, Looking at the next one, you have C complement, then union D complement. This could be written as C intersect what? D, then the complement. Now, when you look at these two, they're disjoint, so they have nothing in what? In common. So meaning the inside here is just going to be the empty set, then complement of the empty set. But then complement of the empty set, as earlier discussed, is just the universal set. So this gives you the universal set. I leave the two to you to discuss. Okay, we come here, I do the first part and I leave the two to you guys. So it's saying using the associative and distributive properties of union and intersection show that, so they want us to show that A is equal to this, and how do we show that? So they're saying we should show that A is equal to A intersect B union A intersect C complement. So using the distributive law and the associative law, I can see that they had distributed here the A intersection because it's common, meaning I can factor it out. I have A intersection is common. Then this part here, I'll have my B, then I have union there. Then here I have B what? B complement. Now, what is this part? What is B union B complement? So if I draw a Venn diagram here and I have my set B, this is B, everything outside here, use a different color, everything outside here, there is the B complement. And when I look at this here, do they have, okay, so when I look at this here, the union of them, the union of what? Of A. So we're saying A, A, okay, so we're saying A, yeah. Oh, the complement, I placed it at the wrong position and nobody was paying attention. So this complement is not there. The complement is here where B is. Okay, so then what does that then mean now for us? So A union B complement. So A union B complement, this just gives us the whole universal set since we're bringing everything now together. So I have A intersect the universal set, which is E or U, but then according to that property which we learned earlier, A intersect B is just going to be what? To be A. And that's how you get A there. So that's why A is there. And I've shown that. So you will do the same for the next two. And okay, we do this. So this last two, this part here. So we're saying X, Y, and Z, and they're telling us to simplify this uh, to as furthest as what as we can. So if I draw a Venn diagram, this time I have three sets. That is, I have X, Y, and Z. Then they're telling me this X complement, meaning everything outside X but is in the universal set. So meaning it's going to be this, apart from the set X, this part here. Okay, so there is what I have. Then they're telling me intersect what? Intersect. So union, the intersection of what? Of Y and Z. So when I look at Y and Z, so this is Y and this is Z. Where do they intersect? They intersect at this point here. So they intersect at this point here. It's where they what? Is where they intersect. So they're telling me now, here we must bring what? All this here, union, or we must combine everything. That is the intersection, this intersection part, and what? And the X complement, and the X complement, which is just this outside part here, including this part here. So now, how could we write that? How could we simplify that further on? Okay, let's look at it. Well, I don't think you could write it in any simpler form, but you could show it like this in a Venn diagram. That's what it means. So in a Venn diagram, if you were to just draw it separately and shade it like that, you will have this part here being shaded, and also the remaining parts here being what? Being shaded also, apart from the set X, apart from everything apart from X only shades this part here. And I don't think you can write that any further. Well, you continue to do further practice. Okay, so now, which gives us to this point where she's the assignment, and that's my phone number there. You can WhatsApp me there, and these are the remaining questions that I was leaving out to say you'll be able to do them. I'll share this in the group, and you will answer. Well, I don't know if there's any question, but this is where we end with our class today. All right, thank you very much, and I'll see you in the next one. All right, so we continue. Then we